All right, welcome back. Module 2. This is where we get down to the nuts and bolts, the real nitty-gritty of how information is actually stored.
It is. It is. And it directly impacts, the performance, the reliability, even the security of all the data that, well, we rely on every day.
So if you've ever, saved a file or wondered what happens when you hit save or thought about data loss, this is the model for you. We're going to break it all down.
Absolutely.
Okay, let's start at the very beginning. We're talking mechanical hard disk drives.
Yeah.
These things have been around forever.
Right.
But how do they actually work?
It's pretty amazing when you think about it, right? You've got these magnetic platters spinning like thousands of revolutions per minute. And then this arm with a read-write head that moves, get this, at 25% the speed of sound to read and write the data.
25% the speed of sound. I mean, that's incredibly fast.
It is. It's mind-boggling, the precision involved there.
But all those moving parts, that's got to be like a recipe for disaster, right? What happens if something goes wrong?
Well, yeah, I mean, there's definitely potential for failure, right? We call it a head crash if that arm were to hit the platter.
Oh, yeah. I've heard that term.
But before we get into, protecting against those, let's actually talk about the parts of the disk itself.
Okay, break it down for us.
So you got these platters, kind of like, think of old records, with these concentric circles called tracks.
Right.
And within those tracks, the data is stored in sectors.
So the arm with the read-write head, it zips around on these tracks, finding the right sector.
Yeah, exactly.
To grab the data.
To access, yeah. And the time it takes to find that right track, we call that seek time.
Oh, okay.
And then rotational latency, that's how long it takes for the platter to spin around to the right sector.
Got it.
And then you have the data transfer rate. And all those things combined really impact, how fast your drive can access and store information.
It's all about speed.
Speed and precision, yeah.
But what about those flash drives, the SSDs?
Yeah, that's a whole different technology.
They are.
Yeah, we're talking semiconductors, no moving parts at all.
Okay.
So significantly faster and more reliable than the mechanical drives.
So that sounds like those are the way to go.
Well, there are trade-offs, right? I mean, they are faster and more reliable, but they're also more expensive per gigabyte of storage.
Oh, okay. So that's the catch.
Yeah. Hard drives are still a cost-effective option, if you need a lot of storage.
Got it.
It really depends what you're looking for.
Makes sense.
Yeah.
So, okay, we've got our disks, spinning or solid state. How do they fit into a larger picture, like a storage system? What does that even look like?
Right. Well, think of it like building a house.
Okay.
You got the foundation, walls, roof, all these different components that have to work together. A storage system is similar.
Okay.
You've got hosts, you got connectivity, and you got the storage media itself.
So the host is like my laptop or like a server in a data center.
Yeah. Anything accessing the data. Exactly. Yeah. Okay.
And even within a host, you've got logical components,
Yeah.
the operating system,
Right.
file systems, volume managers,
Okay.
all working together to manage those requests for data. It's quite a dance.
And connectivity.
Yeah, that's how all this stuff talks to each other.
Right. All those cables and protocols, I don't even know what half of them are.
Right. Yeah, you got buses, ports, cables. Think of it as like the plumbing and the wiring of our digital house.
Okay.
Right.
Yeah.
There's a whole lot of options. IDE, SATA, SCSI.
Fiber channel.
Fiber channel.
I've heard of that one.
Yeah. Each one has its own, pros and cons.
So it's not just as easy as just plugging in a hard drive. There's a lot more going on.
Oh, yeah. A lot more going on behind the scenes. And then, of course, you got the storage media itself. I mean, we've come a long way from punch cards and magnetic tapes.
It's true.
To the disk drives and disk arrays that we use today, the dominant players. So, okay, from my computer to the actual storage media, how does that work? How does that data get there?
Okay, so imagine it's like a relay race.
Okay.
You create a file. It's mapped to these blocks in the file system. Then those are mapped to extents in the what we call the logical volume manager.
Okay.
And then finally, those are mapped to physical extents on the disk.
Oh, wow. So it's not just like going straight there.
Yeah.
It's going through all these different stages.
Oh, yeah. Very carefully orchestrated to make sure everything is stored and retrieved efficiently.
Okay. Now, what about this term I keep hearing? RAID. Redundant array of independent disks.
Yes. Yes.
What is that all about?
It's all about protecting your data,
Right.
right, from disk failures.
Okay.
Especially those head crashes we talked about, like a safety net for your digital life.
So like having backup dancers ready to go if one of the main dancers twists an ankle or something.
Yeah. I like that analogy. Different raid levels or like different choreographies, right? Got some prioritized speed.
Oh.
Others that prioritize data protection. Some try to do a little of both.
Okay. Let's talk about some of these raid levels. What are we looking at here?
So one of the simplest ones is RAID 0.
0.
0, yeah. Focuses on speed by striping the data across multiple disks. Like, having multiple lanes on a highway. Data can flow faster,
Got it.
but there's no redundancy.
Uh-oh.
So if one disk fails, you lose data.
That sounds a little risky.
It can be. It can be. Now, RAID 1,
Okay.
all about data protection. It mirrors your data on a second disk.
Oh.
So if one fails, the other one just picks up seamlessly.
So like having a twin that can step in.
Exactly. But, it comes at a cost. You need twice the storage capacity because you're duplicating everything.
Okay, so RAID 0, fast but risky.
Mm-hmm.
RAID 1, safe but more space.
Yeah.
Anything in between.
Oh, yeah. There's RAID 1 plus 0, or sometimes called RAID 10. It combines mirroring and striping.
Oh, okay.
So you get both speed and redundancy,
Right.
like having two sets of backup dancers, each mirroring the other.
I like that.
But you need at least 4 disks, so can be a little more expensive.
And what about RAID 5? I feel like I hear that one a lot. What's so special about RAID 5?
RAID 5 is where we introduce the concept of parity.
Parity. Yeah.
It's a mathematical calculation that allows you to reconstruct data from a failed disk.
Ooh.
So it stripes data and parity across all the disks,
Okay.
providing both performance and data protection, but less storage overhead than mirroring.
So parity is like, I don't know, like a spare tire in your car.
Yeah, I like that. You don't need it all the time, but when you do,
It's a lifesaver.
exactly. So RAID 5, good balance of performance, protection, and cost. Suitable for a lot of different applications.
Okay, so basically you've got to choose your RAID level based on like what's important to you.
Yeah.
Do you need the speed? Do you need the protection?
Exactly. What are your priorities?
And I guess there's no one right answer.
No, not at all. Depends on the application.
Mm.
And then to add even another layer of protection, we have what are called hot spares.
Hot spare.
Yeah, these are spare disks that are just standing by, ready to jump in if a disk fails.
Yeah.
Minimize that downtime. Minimize data loss.
So they're like the understudies just waiting in the wings.
Exactly, yeah, just waiting for their moment.
Okay, so we're not just stacking up hard drives here, are we?
No. We've moved beyond that. We're in the realm of intelligent storage systems now. Things are getting fancy.
Okay, intelligent storage. What does that even mean?
So they take those basic RAID arrays and they add a lot of sophistication to them. They have things like large caches to speed up data access, advanced management tools, so you can really control everything.
Okay.
And even the ability to do what we call virtual provisioning.
Virtual provisioning? I don't know what that is.
So it's like reserving seats on an airplane, right? You might overbook a little bit, account for no-shows.
Mm-hmm.
But you don't actually have that many physical seats. So with virtual provisioning, you can allocate more storage than you physically have.
Oh.
And the system manages the actual space very cleverly.
Okay, so it's like it knows what it's doing.
Yeah.
It's like a smart system.
It's like the brains of the operation,
Yeah.
constantly analyzing, optimizing how that data is stored and accessed.
This is really cool. Okay. So what are the main pieces of these intelligent storage systems?
So typically you've got a front end, which is the interface between the storage system and the hosts.
Okay.
You got ports for connecting everything, controllers that manage all that traffic.
Okay.
Then you've got a cache, that super fast memory buffer we talked about. And then you've got the back end, which handles the connection to the physical disks.
So it's like this whole dance between the hardware and the software.
It is.
To make sure that everything's running smoothly.
Yeah, to deliver that top-notch performance in data protection.
Okay. And you mentioned LUNs earlier.
Yes, LUNs, logical unit numbers. They're like virtual disks that represent, storage to the hosts in a nice, manageable way.
So instead of seeing a bunch of random disks, the host sees these neat little LUNs.
Exactly. And with virtual provisioning, you can create what we call thin LUNs that appear larger than the space that's actually allocated to them.
Wow. So you're basically making the most of your storage resources.
Exactly.
Yeah.
And then to keep everything secure, we've got LUN masking.
LUN masking?
Yeah, that's like the bouncer at the storage club.
Okay.
Deciding who gets in, who doesn't.
Got it.
So it controls which hosts have access to which OUNs? Prevents unauthorized access, prevents accidental deletion.
Crucial security feature.
Absolutely. So, we've gone from those simple direct attached storage to these really sophisticated systems that manage and protect our data like a well-oiled machine.
It's really amazing to think about all this complexity going on behind the scenes every time we save a file.
It is. It is. And this evolution, it continues, right? We've moved from that direct attached storage, or DAS, where things are directly connected, to full-blown networks dedicated to data. We're talking storage area networks, SANs, and network-attached storage. NAS, the heavy hitters.
The big leagues. Okay, I'm ready to explore this world of network storage.
All right, let's do it. We'll start with DAS, kind of the original setup, right?
Okay.
Storage devices are connected directly to the server.
Okay.
Like plugging an external hard drive into your computer.
Okay.
It's simple, cost-effective, relatively reliable, but it's got limitations.
Okay, so good for small setups, but maybe not ideal if you've got, a ton of data, a lot of users.
Yeah, as storage needs grew, we needed something more. That's where SCSI came in, Small Computer System Interface.
That's CSI.
This was a game changer. Faster data transfer rates, and you could connect multiple devices on a single bus.
So like going from a one-lane road to a multi-lane highway for data.
I like that. And SCSI uses this client-server model. So an initiator device, like your computer, sends commands to a target device, like the storage array. And each command is packaged into what we call a command descriptor block, CDB, which is like a set of instructions for the storage device.
Okay, got it. So does each device on that bus have its own, address, like a phone number or something, so they don't get mixed up?
Exactly. SCSI uses initiator IDs, target IDs, and LUNs to make sure every device has its own specific address.
Okay.
No conflicts. Data gets to the right place.
Makes sense. But as data needs kept growing, we needed something even bigger, right? Even more powerful than SCSI.
We did. And that's where the SANs came in. Storage area networks.
I said SANs, okay.
These are dedicated high-speed networks built specifically for storage traffic.
Okay.
Think fiber optic superhighways.
It's intense.
Oh, yeah, for data. Connecting servers and storage arrays.
Okay.
With incredible speed, incredible efficiency. High performance, scalability, availability, redundancy. I mean, this is for demanding environments.
Okay, break down the pieces of a SAN for me.
Okay, so you've got your node ports. Those are kind of like the on-ramps, off-ramps to our data superhighway. You've got the fiber optic cabling itself, connecting everything.
Mm-hmm.
Then you've got hubs, switches, directors. These are like the traffic control system, making sure everything's flowing smoothly.
Okay.
And then you've got the storage arrays themselves.
Right.
Those massive warehouses of data.
Wow.
That are being accessed, managed, all through the SAN.
So it's this whole complex but incredibly powerful system.
Oh, yeah.
For managing all this data with really high performance and reliability.
It is. Now, how these devices are connected in a SAN, we've got point-to-point connections.
Okay, that sounds straightforward. Point to point. So it's like a direct connection between two devices.
Exactly. Simple, dedicated, but not very flexible and not very scalable.
Okay. What else is there?
Well, there's FCAL.
FCAL.
Fiber channel arbitrated loop. This is kind of like a party line,
Okay.
Multiple devices sharing a single loop for communication. More scalable than point-to-point. But you can only have one device transmitting data at a time.
Oh, so it's like a group conversation where everyone has to take turns talking.
Exactly, yeah. And then you've got FCSW, fiber channel switched fabric, which is the most advanced and most scalable option.
Okay, tell me about SCSW. This sounds like a big deal.
So FCSW uses intelligence switches to create what we call a fabric, a highly efficient network where data is routed directly between devices. No more bottlenecks from those shared loops.
So it's like everyone gets their own dedicated lane to have their conversation on.
Yeah, exactly. Smooth and efficient communication. So FCSW, ultimate solution for high performance, scalable SANs.
Okay, so it's a network that's literally designed for data to move as fast as possible.
Yeah, you got it. And then to manage all this access and security in a SAN, we use a technique called zoning.
Zoning? What's zoning?
So imagine creating these virtual boundaries within the SAN.
Okay.
You're grouping devices into specific zones to control which devices can talk to each other.
So it's kind of like setting up different departments in a company, maybe?
Yeah. Each one with its own kind of access privileges and communication channels. So it enhances security, prevents unauthorized access, and it emulates performance by isolating traffic between those zones.
Okay.
And there's different types of zoning.
Okay.
You got port zoning, WWN zoning, mixed zoning, each using different methods to define those zones.
Okay, so it's like giving you a lot of flexibility in how you manage the access and the security.
Exactly, yeah. So, we've basically built a whole city for our data to live in with its own infrastructure, its own traffic rules, security protocols.
I love that analogy. It really makes it easier to understand. But is fiber channel the only way to connect devices in a SAN?
Well, while Fibre Channel has been, king of the hill, the IP networking world is starting to, make its way into the storage realm.
Okay.
That's where IPSN interworking comes in.
So using our good old IP network infrastructure, like the internet, for storage traffic.
Exactly. And IP networks offer a lot of advantages, right? Easier management, leverage existing infrastructure, lower cost usually compared to that dedicated SAN hardware, multi-vendor interoperability. It's like using the same roads for cars and trucks.
Makes transportation more efficient. I like that. So what are some of the protocols used for this IP SAN interworking?
So two prominent ones are ISCSI,
ISCSI.
Internet Small Computer System Interface. It takes those SCSI commands and encapsulates them within IP packets.
Oh.
So you can send storage traffic over an Ethernet network.
So it's like putting your storage commands in an envelope and sending them through the regular mail instead of hiring a special courier.
Exactly. And then you've got FCIP,
FCIP.
Fiber Channel over IP.
Okay.
That creates a tunnel between two fiber channel networks over an IP network.
A tunnel. So like digging an underground passage for your data to travel securely between two different places.
Yeah, I like that. It extends the reach of your SAN without having to, buy all that expensive dedicated fiber channel equipment.
Okay. And then there's FCAE, Fiber Channel over Ethernet.
Ah, yes, FCAE, taking it a step further, maps fiber channel directly over Ethernet.
Okay.
So merging those car and truck lanes into a single high-speed highway consolidates your network infrastructure, reduces costs.
Wow. These IPA SAN technologies are really changing the way we connect and manage storage. It's all about flexibility, scalability, cost-effectiveness.
It is. Now, we haven't talked about NAS yet.
Right. Network attached storage. What about NAS?
So NAS is like your friendly neighborhood storage provider, offering easy access to files over a network. Think of it like a shared folder on a network drive that multiple users, multiple devices can access.
So it's like a central hub for all your files. Makes it easy to collaborate, to share information.
Exactly. Dedicated file servers optimized for storing, sharing files. They're like specialized appliances.
So how are they different from just regular servers that can also share files?
So NAS devices, they have their own operating systems. They often have dedicated hardware, RAID arrays, high-speed network interfaces. They're much more efficient, much higher performing for these file-serving tasks.
So they're like the professional athletes of file sharing.
Yes.
Whereas regular servers are more like the weekend warriors.
I like that. And NAS devices offer a whole bunch of advantages, right? Improved efficiency, flexibility, centralized storage, simplified management, scalability, high availability, security integration. I mean, you name it.
It's a lot of perks.
It is. And they use these file sharing protocols like CIFS, common in Windows environments, and NFS, Unix environments, to let clients access those files seamlessly.
So they can talk to different operating systems.
Yeah, exactly. And typically they have storage interfaces like SCSI or Fiber Channel to connect to the storage arrays where the files actually live.
Okay.
So it's a complete package, from the software to the hardware to the connectivity.
Wow.
And there are two main implementations. You've got integrated NAS, where everything's housed in one unit, and gateway NAS,
Okay.
where the NAS head acts as a gateway between the network and a separate storage array. Yeah.
So whether you need a simple file server for your home office or a massive system for a huge enterprise, there's a NAS solution out there.
There is.
Amazing how many options there are for storing and managing data these days.
It is. And speaking of managing data, let's talk about replication.
Replication.
Yeah.
We touched on it with RAID, but I feel like there's a whole lot more to it. What exactly is data replication?
So it's the process of creating a copy of your data, right?
Okay.
Essentially a backup, a mirror. Think of it as insurance for your data.
Okay.
Right?
Okay.
You can recover from accidental deletions, hardware failures, even, catastrophic events.
So it's like having a spare key to your house just in case you lose your main one. Or a backup generator that kicks in if the power goes out.
Yeah, exactly. And you can use replication for a bunch of things, right?
Hmm.
Backups, disaster recovery, business continuity, testing, data migration, all about making sure your data is safe, secure, and available when you need it.
Okay, starting to see how important this is.
It is. It is.
Now, you mentioned consistency earlier.
Yes.
What does that mean in the world of replication?
So consistency is crucial because it ensures that the replica is a true copy of the original.
Okay.
Right.
Right.
All those changes made to the original have to be reflected accurately in the replica. Otherwise, you could end up with corrupted data or applications that just don't work properly.
So it's like making sure your backup is a perfect mirror image of the original. No distortions or missing pieces.
Exactly. And there's different ways to ensure consistency,
Right.
depending on whether you're dealing with file systems or databases.
Okay, let's start with file systems then.
All right, so with file systems, one way is to take the file system offline.
Offline.
Yeah. Unmount it before creating the replica. That ensures that all the changes have been written to disk, so you have a clean snapshot.
So it's like pausing a movie and taking a picture of the screen. You get a clear, static image of that particular moment.
Exactly, yeah. However, taking the file system offline can disrupt operations.
Right.
So another option is to keep it online, but flush the host buffers before you create the replica.
Flushing the buffers, what does that mean?
So file systems often store data temporarily in memory.
Okay.
These are called buffers to improve performance. Flushing the buffers forces all that data to be written to disk, so the replica captures all the latest changes.
So it's like making sure everyone's boarded the train before it leaves the station.
Yeah, nobody gets left behind. But databases, those are a bit more complex. They're
Right.
constantly being updated with transactions, so ensuring consistency during replication is trickier.
Right, because they're always changing.
Constantly changing. So how do we handle database replication without causing chaos?
Yeah, how do you do that?
Well, one way is to take the database offline. Shut it down before creating the replica. It'll ensure consistent copy, but it also means downtime.
Downtime's a big deal, though.
Oh, huge.
Right.
Especially for businesses that rely on their databases 24/7.
Right.
So the alternative is to keep the database online. And we use techniques like what's called the dependent write I/O principle, or holding I/Os, to ensure consistency.
Those sound pretty technical. Can you break them down for me a little bit?
Sure. So think of the dependent write I/O principle as a very strict recipe for baking a cake.
Okay.
You got to add those ingredients in the right order, otherwise you end up with a mess.
Right.
So it guarantees those transactions are completed correctly in the replica, even if it's created while the transactions are still in progress.
Got it. What about holding IOs?
So holding I/Os is like hitting the pause button on a movie.
Okay.
You're temporarily stopping all write operations to the database while the replica is being created
Okay.
to ensure that consistent snapshot.
So you freeze time to capture the perfect copy.
Exactly. And then to manage consistency across multiple devices, multiple arrays, especially when we're talking about remote replication, we use something called consistency groups.
Consistency groups.
Yeah. Imagine a band playing a song, right? Everyone needs to be in sync.
Right.
So consistency groups, they define a set of devices that need to be replicated together to maintain consistency for, say, an application.
So it's like making sure all the band members are playing the same notes at the same time, even if they're in different rooms.
You got it.
Wow.
So no matter what, even if there's a network hiccup or some kind of component failure, everything stays in the right order.
Okay. So we've talked about how to ensure consistency. What are the actual technologies used for local and remote replication?
Right. So let's start with local replication, where replicas are created within the same array or data center.
Okay.
We've got two main types, host-based and array-based.
What's the difference?
So host-based uses the host computer's resources to create and manage those replicas, while array-based relies on the capabilities of the storage array itself.
So it's like doing your laundry at home versus sending it out to a service.
Exactly.
Got it.
Host-based, often simpler, less expensive. Array-based, more advanced features, often better performance.
Okay, let's talk about some host-based technologies. What are some common ones?
So one common one is LVM mirroring. The logical volume manager creates a mirror copy of a logical volume on a separate disk, like having a backup hard drive mirroring everything on your main one.
Makes sense.
Another common one is file system snapshots. They create this point-in-time view of the data, and they're often pointer-based, meaning they only track changes since the snapshot was created. Very efficient storage-wise.
So it's like having a list of edits to a document instead of creating a whole new copy each time.
Exactly. Now, array-based, you have full volume mirroring.
Okay.
The whole contents of a source volume are mirrored to a target volume, a separate array.
So it's like a complete clone of your hard drive on a different device.
Yeah, exactly. If one fails, you just switch to the other one. Provides that high availability. And then you have what's called pointer-based full volume replication. Similar, but initially only creates pointers to the data, only copies the actual blocks when they are modified.
So you're like creating the blueprint of a house.
Yeah.
Instead of building the whole thing, and then only add the bricks and mortar when you actually make changes.
That's a great analogy. And then pointer-based virtual replication takes it a step further.
Okay.
Only storing those pointers. And copying blocks when they're modified using this, what we call copy on first write technique.
So you're really only using storage space for the changes, not for the whole duplicate.
Exactly. Maximizing that efficiency, maximizing performance.
Okay, so that's local replication.
Mm-hmm.
What about remote replication?
Remote replication. That's where we're creating copies of data at a different location.
Okay.
Like a separate data center or a geographically distant site. Helps protect against regional disasters. Ensures business continuity if something happens.
So it's like having a backup bunker, just in case your main base gets compromised.
Yeah, exactly. And there are two main modes, synchronous and asynchronous.
Okay. What's the difference?
So synchronous is like having two perfectly synchronized dancers
Okay.
mirroring each other's moves in real time. Every write operation is committed to both the source and the target before it's even acknowledged to the host.
So it's like a live video call, maybe?
Yeah, everything's happening simultaneously on both sides.
Okay.
So it guarantees that data is identical at both locations, but it can impact performance.
Right, because you're waiting for that confirmation.
Yeah, that write operation has to wait for confirmation from the remote site.
Especially if those sites are far apart. What about asynchronous?
So asynchronous is more like, two dancers performing similar moves, but not perfectly in sync. So the write is acknowledged to the host as soon as it's committed to the source storage. And then the data is replicated to the target later in the background.
So it's like recording a dance practice.
Yeah.
And sending the video later instead of live streaming it.
Exactly. It minimizes that performance impact. But there is a delay between the source and target data. That delay is what we call the recovery point objective, or RPO. Represents the amount of data you could potentially lose if a disaster happens.
Right, so you're trading off performance for that potential data loss.
Yeah, synchronous. Lowest RPO, but possible performance hit. Asynchronous, better performance, but higher RPO.
So it really depends what's more important to you.
Exactly. And with asynchronous, how do we actually make sure that replica stays in sync?
Right. If things aren't happening at the same time,
Yeah.
how do you keep everything consistent?
Good question. Some vendors use what's called write ordering. Every operation is tagged with a timestamp and a sequence number,
Okay.
like adding page numbers to a document. Make sure those updates are applied in the right order, even if they come in out of order.
That's clever. It's like making sure all the pieces of a puzzle end up in the right place.
Yeah, you got it. Others use the dependent write consistency principle. All the writes related to a transaction, they're grouped together, replicated as a single unit, like packaging all those cake ingredients together.
Okay, so no matter which way you do it, the goal is to make sure the data is accurate and consistent.
Exactly. Now remember, with asynchronous, that replica is always lagging behind the source a little bit. That time difference, that's your recovery point objective, your RPO.
Right, how much data you might lose.
Exactly. You can adjust it based on your tolerance for data loss.
Okay.
Smaller RPO means less potential data loss, but you need more frequent replication, which can impact performance.
So you're always balancing, that data protection with how well things are running.
Exactly. You got it. Now, moving on to a little bit more advanced concept, continuous data protection.
CDP.
Continuous data protection. That sounds pretty serious. It is. It is. The goal here is to achieve what we call zero RPO, meaning no data loss.
Wow.
It's like having a surveillance camera recording every single move. You can rewind to any point in time and see what happened.
That's pretty impressive. How does it actually work?
So these CDP appliances, they sit between the host computers and the storage arrays,
Okay.
capturing every write operation in real time, replicating it to a separate storage device. It's like having a backup copy created every time you hit save.
It's like a time machine for your data.
Yeah, you can go back to any point and recover your data exactly as it was at that moment.
That is really cool. So CDP, it's the ultimate data protection solution.
It's pretty amazing, but keep in mind it does come with some trade-offs.
Okay.
Higher costs, more complexity compared to those traditional replication methods.
Well, it's not the right solution for every situation.
Yeah.
But for, like, mission-critical applications.
Exactly, where data loss is not an option.
Right. That's when you break out the big guns.
Exactly. Now, I want to emphasize, replication, it's not just about technology.
Right.
It's about understanding your data, understanding your business needs,
Cool.
understanding your risk tolerance.
So you're not just throwing the most expensive thing at it. You're figuring out what you need.
Exactly. And it's crucial to have a disaster recovery plan in place, outlining how you'll use that replication to recover your data, to get things up and running if something happens.
Having a plan is so important.
It is. It is.
It's not enough to just have the technology.
Absolutely. Now, moving on, we've talked a lot about replication.
Yeah.
But there's another area we need to explore. Networked storage.
Networked storage, we've already covered SANs and NANs.
We have. We've touched on the basics, but there's a whole lot more to it.
Yeah.
We need to delve deeper into the protocols, the architectures, security considerations. It's a fascinating and complex world.
Okay, I'm ready to dive in. What are some of the key things we need to understand?
So we need to understand the evolution of storage architectures. From DAS to SAN to NAS, the different protocols, fiber channel, ISCSI, NFS, and security, of course.
Yeah, that's a big one.
Huge. We're exposing our data to the network.
Right.
Got to understand the risks.
What can we do to mitigate those risks?
So we'll talk about access control lists, encryption, secure protocols, all that good stuff.
This is going to be exciting. It sounds like a whole new world to discover.
It is. We'll revisit the basics of DAS, SAN, and NAS. And then we'll really get into the nuts and bolts of those protocols, the architectures, the security. It's all critical for modern data management.
Right, network storage. We left off talking about getting into the nuts and bolts of how it all works.
Yeah, let's revisit those storage architectures.
Oh.
Remember, we started with DAS, direct attached storage.
Right, like plugging a hard drive right into your computer.
Exactly. Simple, but not very scalable.
Right, so as our data needs grew, we needed something more.
Exactly. We needed something bigger, something better. That's where SANs came in. Storage area networks.
Those high-speed networks dedicated to storage.
Connecting servers and storage arrays with crazy speed and efficiency. We're talking fiber optic superhighways for data.
Right, high performance, high availability, redundancy. It's all there with SANs.
It is. It is. And then, of course, we've got NAS, network attached storage.
The friendly neighborhood storage provider.
That's a good way to put it. Makes it easy for users to access and share files.
Dedicated file servers optimized for all that sharing and storing.
Now let's talk about the protocols that make all this possible. Fiber channel, that's a big one.
Right, that's the one that uses those optical fiber cables for super fast data transfer, right?
Yeah, it's the backbone of a lot of SANs, especially when you need that low latency and high bandwidth for performance-heavy applications.
But you mentioned earlier that IP networks, like the internet, are also being used for storage.
Right, we're talking about ISCSI, Internet Small Computer System Interface.
ISCSI. So we're using the internet's infrastructure for storage communication.
You got it.
That seems pretty convenient.
It is. Easier management, often lower cost. You can leverage your existing network.
Makes sense. And what about NFS network file system?
Ah, yes. NFS, another popular one, especially in those Unix environments. Simple, efficient for sharing files over a network.
Okay, so we've got a whole toolbox of protocols, each with its own strengths and weaknesses.
Exactly. It all depends on your specific needs. What are you trying to achieve? Now let's talk about architectures for a second.
Okay, architectures. So we know DAS is limited because the storage is directly attached to the server.
Right. It's like having a small library in your house. It works for a while.
But what if your book collection grows?
Exactly. You need a bigger library.
You need to expand. That's where SANs and NAS come in.
You got it. SANs centralize everything, like a giant public library with high-speed connections to all the branches.
So multiple servers can access the same storage.
Exactly. Better scalability, better efficiency.
And NAS, those are like the specialized sections for lending and borrowing.
Exactly. Focus on file sharing. But no matter what architecture you choose, security is paramount. We're putting our data out there on the network.
Right. That's a big concern. How do we protect everything?
Access control is key. We can use access control lists, ACLs, to specify exactly who can access what.
So not everyone gets a library card.
Not everyone, no. Only authorized users. And we can encrypt the data both in transit and at rest. An extra layer of protection.
Like putting those sensitive documents in a locked briefcase.
Exactly. And using secure protocols like SSH for remote access.
Makes sense. So it's been a fascinating journey through the world of networked storage. Architectures, protocols, security, the whole 9 yards.
It has been. From those simple direct attached setups to the complex networks we have today, it's incredible how far we've come.
And I think our listeners are walking away with a much better understanding of how all this works, how their data is stored, accessed, and protected.
Absolutely. And hopefully they can now make more informed decisions about their own data management, whether it's personal or professional.
And that's what it's all about, right? Empowering people with knowledge.
It is. And as you continue to learn about information storage, remember that it's always evolving.
Right. New technologies and new challenges are popping up all the time.
So stay curious and keep learning. The world of data is waiting to be explored.
And on that note, we'll wrap up our deep dive into Module 2. Thanks for joining us, and we'll catch you next time for another exciting exploration of the world of information storage.